So this week we're going to talk about harmonic motion. And if I had to give you a street definition of harmonic motion, I would say it is back and forth or up and down. So the way it is different from a trajectory is it returns to its original position and does it over and over again. We're going to talk about harmonic motion with a mass on a spring. It's a standard way you begin to look at it. Here we have a mass, 500 grams, hanging from a spring, and you know that this will experience a force F equals minus kx. So if I pull the mass down, the spring tries to pull it back. And if I push the mass up, the spring tries to push it back down. So we know, we've talked about springs. F equals minus kx is Hooke's law, always pushing the mass back to its resting position. So let's think about what we would calculate. So we'd say, well, Newton's second law still applies. Sum of the forces equals mass times acceleration. And you'd say, okay, let's plug in. The only force we're going to deal with is Hooke's law, and there's gravity involved, but let's pretend we're doing it sideways. Let's just write minus kx equals mass times acceleration in the x. And this becomes already difficult to deal with. When you did kinematics, you often had a constant acceleration down. The only force you dealt with is gravity. But now we have an acceleration that isn't constant, and actually the force, and therefore the acceleration, depends on where you are in x. So this is mathematically a whole new thing to deal with. We could make an attempt at it. We could say minus kx equals m, and acceleration is the change in velocity with respect to time, delta velocity over delta t, but delta velocity is delta x over delta t. So you can make some mess like this. We don't want to deal with this. You know why? This is a differential equation. If you are just now learning to be afraid of calculus, you don't even yet know how afraid you should be of differential equations. Not really. Differential equations are wonderful. Differential equations is really what led us to all the kinematics formulas we told you about, right? So if you recall, x final equals x initial plus v x naught t plus 1/2 at squared. Really, that was the solution of a differential equation. That was just the case where you have a constant force like mg creating this acceleration. Then we solved the differential equation to get this. In this class, we just gave it to you, and we did some geometry to talk about it, but really that's all it was. Well, now we have a new differential equation we have to solve. And what this means is, it is a fundamentally different equation. So a fundamentally different equation, it's called the equation of motion because it describes the motion. So if we have a fundamentally different equation of motion, we get a fundamentally different motion, as you would expect. And let's look at what the fundamentally different motion is. If I get it moving, you know what it's going to do. It moves up and down like that. It's not a trajectory. It's not falling. It's something completely new. It's harmonic motion. Harmonic meaning it's moving in sort of a sinusoidal pattern. Okay? So, not too surprisingly, the solution to this differential equation is also sinusoidal motion. So if we were to plot it, we've been doing lots of x versus time plots. It would look something like this, sinusoidal motion. And if we were to write the equation, it would look something like this. The position versus time solves that equation is a sine 2 pi f t, sinusoidal motion with respect to time. And some of these variables and formulas you might be familiar with. This is a sine function. You might see it as just y equals sine of x. Well, this is the kinematic version. That position x is sine of something times time. So the thing showing up in here, one is the amplitude. So that's how high it gets above 0 and how low it gets below 0. So that's the amplitude, how far it goes from the 0 line. And the frequency is related to how fast it goes. So the way you can measure how fast it goes directly off the graph is actually not the frequency, but the period. t. So the frequency is 1 over t, and t is the period. T is in seconds. It's the actual time that you would measure in between two peaks, or it's the total amount of time of one cycle of the sinusoid. Right? So this is a sinusoidal curve. An entire cycle goes from the baseline up and then back. That's an entire cycle. Or you can draw a cycle from the top to the top. You can see those are repeating cycles. So the period is the length of a cycle, amplitude is the height. We often think in terms of frequency in hertz, periods in seconds, and f is in hertz. And this is just how it works out. If we could really solve this differential equation, this is what we would get.